Okay, so let's continue with our discussion, which is whose aim is to define what a regular function at a point is. Okay, so let me again go back to this definition. The definition says that you have a function f with values in k, the base field, and it's defined in an open set containing the point small x. Of course that open set could be that open set is being considered as an open set in the affine variety or quasi affine variety in which x sits. Okay, and we say the function f is regular at that point if it is if it can be written as a quotient of polynomials. Okay, that is there are two polynomials whose quotient will define a function. A quotient of polynomials will define a function into the field, the base field, the scalar valued function, wherever the denominator polynomial does not vanish. That's actually so this a function of the form g mod h, where g and h are polynomials, will always define a function on dh, on this basic open set dh, which you know in its own right is actually an affine variety. And the fact is that you'll just have to find a point a h such that dh intersection x, capital X, contains small x, and which is possible because it's basically because any open set is a finite union of such dh's, okay, for various h's, right, which is a fact that we already seen. In fact any open set here is the complement of a closed set, and that closed set is given by the zero set of an ideal, and that ideal is finitely generated, and therefore that closed set is given by the intersection of the zero sets of the generators of the ideal, and therefore its complement is given by the corresponding union of basic open sets, namely the loci, the open sets where the corresponding generators of the ideal does not vanish individually, it's the union of that. Okay, that's how every open set is a finite union of basic open sets, and therefore this is my definition, and this definition seems to be correct for if you look at a basic open set. A good function on this is of that form. Okay, but the point is that whenever you make a pointwise definition, what you are actually doing is you are gluing. Okay, and the problem with gluing is that it can produce new objects, if you glue objects of a certain type, it can produce a completely new object. Okay, so if you glue functions locally, you might get something which is very different from what an ordinary function is. For example, if you glue topological spaces in a funny way, you might get a topological space that looks very different from the ones that you started with. Okay, we are going to see later that if you glue affine spaces, finitely many affine spaces, you can get a projective space. Okay, so for example, if I take 2 copies of the if I take for example the usual topology and take 2 copies of the unit disk on the real plane, and if I make them look like 2 hemispheres of a sphere and then glue them like this, I'll get a sphere. Okay, and the point is that the new topological space I have got, which is a sphere, is very special because it is compact, which is not a property that is shared by either of the 2 open disks I started out to glue it. So the problem is that gluing of objects in mathematics can produce new objects which have properties that are completely different. Okay, the same thing happens also when you try to glue functions, and what I am saying is that whenever you make a definition pointwise, you are actually doing some gluing, and then for all you know, you might ask the following thing can happen. If I look at all the functions on affine space itself which are regular at every point, they could be very well different from polynomials. What is the guarantee that they are no different from polynomials? But the answer is that you are not going to get anything new. Okay, and that's a surprise, and it's a pleasant surprise, and that's what we are going to prove. Okay, so let me try to explain that. So just to stress this gluing business, let me write out. So let me make a few let me make a few notational conventions. So what I am going to do is x in an k and affine variety or a quasi affine variety so let me do the following thing. Let me do it one by one. Let x in A and be an affine variety. I define O of x to be the regular functions, the set of regular functions on x. Okay, and so you see this is the new notation I am using. This is a calligraphic O. Okay, for regular functions, because as yet I do not know anything about a global regular function except that it is locally a quotient of polynomials. Okay, and certainly I don't expect it to be anything, I can't expect it to be anything unless I prove something about it. Okay, so and similarly if u inside x inside an, so this is irreducible closed, and then u is an open inside this irreducible closed, and u is a quasi affine variety. So a quasi affine variety is supposed to be just an open subset of an affine variety. Then again O of u is defined to be regular functions on u. Okay, and these are global definitions. Okay, and how do these global definitions come? They come from local definitions, pointwise definitions. Okay, and so let me write down what is the definition of. So for example, if you suppose I write phi belongs to OU, means what? Means, okay, phi is a map from U to K, is a map that is regular at each small x in U. Okay, of course I am writing this for U, but I can as well write it for the same thing will also work for x, where x is a actually an affine variety, okay, but I am taking a quasi affine variety, right. So what is a regular function on a quasi affine variety? It's a function which is with values in the field, which is just a map, but with the property that it is regular at every point. That means what? So for every x in U, there exists polynomials gx hx in k of x1 etc xn, where of course your u is being considered in x, u is being considered inside x, which is being considered in some in an, okay. Your u is an open subset of x, capital X. It's a quasi affine variety and it's being considered in some affine space. It's an irreducible closed subset of some affine space, and there are polynomials such that d of hx contains x, and phi is the same as gx by hx on dhx. This is the you see, this is the definition on dhx, or rather I should say dhx may not be all of on an open neighborhood of small x contained in d of hx. This is what it means. For give me a point x, I can the function phi in an open neighborhood of that small point small x is the same function that I would get if I evaluate a quotient of polynomials with the denominator polynomial not vanishing and the polynomials being taken in the appropriate number of variables in which dimensional affine space you are considering u and x, okay. So you see this definition is you see, this is a problem with this definition. The problem with this definition is it's so arbitrary in a certain sense. See, I could have, you know, the same space, the same affine variety x could sit in so many affine spaces. See, if x for example is a 2 plane, then x could be a2, or x could be 2 plane in a3, maybe the xy plane, or it could be the 2 plane in some an, it could be anywhere, and depending on where it is I have to take polynomials in as many variables, and then I have to take a quotient. So you see, it's there is so much arbitrariness in this definition, there is so much arbitrariness in this definition, and that sometimes is a little scary, okay. But the point is that you have this for every point x. So now you see, note that the dhx where x is in x, where x is in u, is an open covering of capital X, right, because I said for every point small x I am getting this hx such that the affine open set dhx contains x, okay, and this affine open set, basic affine open set dhx is considered in this affine space, that affine space of that dimension in which is that number of variables in which number of variables you have taken the polynomial hx, okay. And of course, since I say this such a hx exists for every x in u, it means that all these dhx's they cover u, okay. But then what do we know about the Zariski topology? We know that it's quasi compact. Therefore what it will tell you is that out of this collection of hx's I can just be content with having only finitely many, okay. So by the quasi compactness of u, okay, u is after all a subset of x which is in turn a subset of an, and then you know when you take subsets and take the induced topology, the Noetherianness goes down, it is hereditary. So U becomes a Noetherian topological space, and you know a Noetherian topological space is quasi-compact as we saw in the last lecture. So U is quasi-compact, and that means that every open cover has a finite subcover. So what it means is that there exists x1 etc xm in U such that U is DHX1 intersection, sorry, union, U is contained in the union of all these DHXI, HXM, and well, of course phi restricted to phi phi is GXI by HXI in a neighborhood of Xi contained in D of HXI for every I. This is what it means. So you see what it means. So what it means is when you say that you are having a regular function, what it means is that you are actually taking quotients of polynomials and finitely many such quotients such that these quotients they agree on the intersections. You see, if you take the intersection of DHXI with DHXJ, then in that intersection phi will locally be both GXI by HXI, and it will also be equal to GXJ by HXJ. So what you are saying is, you are saying that a general regular function is simply gotten by taking finitely many quotients of polynomials with the property that these quotients of polynomials agree, the functions that they define upon evaluation agree on these intersections, okay. And this is exactly what gluing is. Gluing is you take functions locally and then so many functions with a certain property glue to give a bigger function. If they all give on the intersections, the functions should agree. So what you are saying is just take finitely many quotients of polynomials such that the locus of the non-vanishing of the denominator polynomials covers your space, that is U in this case, and such that these quotients wherever the loci where the denominator polynomials do not vanish intersect, the quotients evaluate to the same function, okay. This is what a regular function on U is, okay. It is got by locally. So what you a global regular function, on an open set is actually gotten by gluing finitely many quotients of polynomials. So it is a gluing process. And now so this is how it is for U. It is the same definition. Instead of U I can put capital X also. The same definition works for any subset, in fact, if you want, of affine space. But in fact, instead of U I could have put any subset of affine space, okay, and I could have said regular functions on that set. But we are interested only in regular functions on either open sets or on closed sets. Either they should be regular functions on irreducible open sets, they are open subsets, that is either they should be we are interested in functions on either irreducible closed subsets, that is functions on affine subvarieties, or we are interested in functions on open subsets of such affine subvarieties, okay. So U is an open subset of X, and of course whenever I am considering a subset I am certainly not looking at the empty set. So U is a non-empty open subset, and mind you a non-empty open subset is both irreducible and dense, okay, because capital X is both irreducible and dense, I mean because capital X is irreducible, okay. So you see what we have defined as regular functions is something that is very strange. It's these are gotten by gluing finitely many quotients of polynomials. So now I can ask, what will I get if I put O of, if I apply this O to an itself, what will I get? If I apply O to dh, what will I get? If I apply O to x, what will I get? If I apply O to dh intersect x, what will I get? The answer is very beautiful. The answer is you will get exactly what you will get if you apply A. Okay, that's the beautiful thing. Okay, and the fact is that is the sophisticated way of saying that is that describes that's why all the 4 are actually affine varieties. Okay, so in more general algebraic geometry you can define the A for objects which are affine objects, okay, and then you can define the O for any general object, and then the theorem is that a general object is an affine object if and only if the O is the same as the A, okay, and that is exactly what is happening here, alright. So I mean that is saying it in very loose terms, okay. To understand the exact import of that statement you should study scheme theory, which should be a second course in algebraic geometry, okay, but nevertheless does not do any harm in my stating it here. So if at all you go ahead to study scheme theory, you can come back and try to remember this statement, okay. So let me make that let me make this remarkable statement. So here is theorem O of an is equal to A of is isomorphic. I should say, okay, let me put isomorphic. So here is the theorem. The theorem is that what you define as regular functions are going to give back exactly these functions which are given when you apply A to these objects, either affine space or affine varieties or basic open subsets of affine space or basic open subsets of affine varieties, okay. This is the statement, right. So the technique of proof is literally the same. Basically it's a technique in commutative algebra. So what I will do is let me first prove the first one, and in fact you can see that you can deduce the remaining if you are a little careful and just apply the same philosophy as the proof of the first, okay. So what I will do is let me prove let's prove O of an is isomorphic to A of A. Let's prove this, alright, let's prove this. So how does one do this? So what I will do is I will do the following thing. So I will define a map A of an to O of an by very simple map. Take the A of an is just the polynomial ring in n variables over K, and simply send the polynomial G to the function G from an to K. So it's a very simple map. So what you do is take an element here. What is it? It's a polynomial in n variables over K, and a polynomial in n variables over K is a function. It's a function from an to K by evaluation. You can evaluate the polynomial at every point, and that is in certainly a regular function, because a regular function is something that is locally given by quotients of polynomials, and this is globally given by a single polynomial, and this single polynomial g can be written as g by 1 if you want. You can think of this g as g by 1, and the locus where 1 does not vanish is everything, okay, and therefore it is also a regular function. So all I am just trying to say is that every polynomial is certainly a regular function, there is no doubt about it. A regular function is something that locally looks like a quotient of polynomials, but something that is globally a polynomial is also a regular function, because it is a polynomial divided by 1 if you want, and 1 is a constant polynomial, which always makes sense, okay. Now the fact is that, you see, just like all the polynomials form a ring, you can add two polynomials, you can multiply them, and then they form a vector space over K, and then so the ring of polynomials is a K algebra, okay, it is a finitely generated K algebra. In fact, it is a free polynomial algebra in so many variables. In the same way, the ring of regular functions is also the set of regular functions is also a ring. That is the first thing you have to realize, because you see, you take sum of two regular functions, okay, the sum will also be regular, because if you take a regular function is locally given by a quotient of two polynomials, and if you take two such regular functions and add in a suitable neighborhood the corresponding quotients of polynomials, the sum of quotients of two polynomials is again a quotient of two polynomials, okay, in the correct neighborhood where the denominator does not vanish, and the product of two quotients of polynomials is again a quotient of polynomials, right. So the moral of the story is that when I define this O of something, whatever it is, the regular functions on that thing, that is a ring. In fact, that is a K algebra. It has addition, it has multiplication, it is a vector space over K. You can easily see that if you take a regular function and multiply it by a scalar, the result is again a regular function, because locally you are just multiplying the numerator polynomial by that scalar, okay, in the expression locally as a quotient of polynomials for that function, okay, and it is also clear that that is a K algebra and so on. So these isomorphisms that I have written here, they are not just isomorphisms of rings, they are isomorphisms of K algebras, okay, they are isomorphisms, they are ring isomorphisms, they are isomorphisms of vector spaces also, okay, that means scalars go to scalars, lambda a scalar lambda in K thought of as a constant polynomial, lambda goes to the same constant function lambda thought of as a regular function, okay. So these are all K algebra homomorphisms, okay. So this map that I have written here is actually, it is very easy to see that, it is obvious to see that it is a ring homomorphism, because G f G1 plus G2 what G goes to and what I mean this association will preserve addition multiplication, it's K linear and all that. So this is a ring homomorphism, it is a K algebra homomorphism, okay. And then the fact I want to make is that I will have to prove two things. I will have to prove that this is injective, I have to prove it is surjective. If I prove that, then I get that this is an isomorphism of K algebras, which is what I want, okay. So it is, so let me write that it is a K algebra homomorphism, that is obvious, no doubt about that. Then how do you show it is injective? It is injective. Why is it injective? Well, if you take two polynomials G1 and G2 which as functions are different, it means that there is a point in An where the values of G1 and G2 are different. That means the difference polynomial G1 minus G2 does not vanish at that point, okay, and that should tell you that G1 and G2 cannot be the same, okay. So it is very clear that it is injective, the injectivity is just very trivial, okay. In other words, I'm another way to say it is that I am saying that if you take a polynomial and if I evaluate it as a function, and suppose as a function it is a 0 map as a function, then the polynomial has to be the 0 polynomial, okay. So this is something that is obvious. Probably it just requires the fact that the field K is infinite, okay, which is true because the field is an algebraically closed field and an algebraically closed field is infinite, okay. Of course the problem is over finite fields you can always find polynomials which are non-zero polynomials but which evaluated as functions end up being the zero function, okay. That can happen for finite fields, but small k is not a finite field, it is an algebraically closed field, and an algebraically closed field is always infinite. And for an infinite field, if you have a polynomial which if upon evaluation it is the zero map, then the polynomial has to be the zero polynomial, okay. That is the statement that is injective, okay. But what is really crucial is the fact that it is surjective, so that requires a little bit of proof. So let me do that. So that is where a little bit of commutative algebra will come in, and you will recognize what is going on if you have done a course in an earlier course in commutative algebra, and where you have proved that you know you have proved the quasi compactness of the Zariski topology when you take the prime spectrum of a ring, okay. So so let me do this. It is surjective, so what I will do is I will start with, so let phi be a regular function, okay. Take a regular function, right. So phi is a map from an to k, and by our definition of what a regular function is, there exists finitely many points, okay, and such that the union is the whole affine space, and such that phi is quotient of polynomials in this sense, okay. So let me write that down. There exist points xm such that an is d h1 h sub x1 d sub h xm, okay. Where hx1 through hxm are polynomials in n variables, and phi is equal to g xi by h xi on d h xi for every I. And of course gx1 through gxm, they are also polynomials in n variables, okay. This is from the definition of what a regular function is, okay. Now you see the first thing is that this has a meaning in terms of commutative algebra. The meaning that it has in terms of commutative algebra is that the ideal generated by the hxi is the unit ideal, okay. So this means commutative algebraically, so you know it is a translation of all these geometric facts into commutative algebra, okay, and you extract some information from commutative algebra. So the fact that A is the union of all this means that the ideal generated by hx1 etc. hxm is 1, is ideal generated by 1, namely it is a whole polynomial. Okay, this is the first thing that needs to be noted. And why is this true? Why this is true is because, well, if this ideal is not the unit ideal, then it's a proper ideal, and then we know that every proper ideal is contained in a maximal ideal. Okay, and you know the maximal ideal is corresponds to a point. Okay, so what will happen is that that point will have some coordinates. Okay, but that point will be here, it's a point of an, so it has to be in one of these. So that means that at least one of the hxi's does not vanish at that point, but that will contradict the fact that this is contained in the ideal of that point. Okay, so this is exactly what I am going to prove. If not hx1, the ideal generated by hx1 etc. hxm is contained in a maximal ideal which is of the form say x1 minus lambda 1 etc. x n minus lambda n. Okay, this will tell you that you see, it will tell you that so you know, if I apply the z, if I1 is contained in I2, then z of I1 contains z of I2, where z is the operation that associates to an ideal its 0 set. So this will tell you that z of hx1 etc. hxm contains z of this maximal ideal, which is actually the point which is actually simply the point, the singleton point lambda 1 through lambda n. Okay, alright. That means what this tells you is that this point is you know, it tells you that this point is a common this point is a common 0 of all these h's. Okay, and if this point is a common 0 of all these h's, that contradicts this statement, because this point is here. Okay, and by definition every point here has to be contained in some locus where a certain h doesn't vanish, but then you are saying that I have been able to find a point which is not in any of these. Okay, it's a contradiction. To an is equal to dh1 dhx1 union dhxn xm. Okay, right. So the moral of the story is that indeed the idea, this condition, the fact that the affine space is a finite union of certain basic affine open sets means that the equations corresponding to those basic affine open sets, those polynomials actually generate the unit ideal. Okay, so what all this will tell you is that this generate the unit ideal. So what it will tell you is that there exists you know, let me give some other names. Okay, so let me use f's. So there are f1 etc. fm polynomials in n variables such that sigma fi hxi is equal to 1. I get this. Okay, in other words, the 1 is in ideal generated by the his, so 1 should be generated by a ring linear combination of the his, and that is what I have written here. These fi's are ring elements, the coefficients from the ring. Okay, so of course I is equal to 1 to m. Okay, now you see Now the point is that I will have to show that let us go back to what I started with and what I want to show. I started with a regular function on an, okay, and I am just trying to prove surjectivity of this map. So I am started with something here, a regular function on an, and I am trying to find that show that it comes from here. So I will have to cook up a polynomial which is equal to that function, okay. So I will have to use this information to cook up a polynomial g such that if I consider g as a map I get this phi. That is what I will have to do, okay, and that's pretty easy to see. So the trick is you multiply both sides by phi, okay, multiply both sides by phi, okay, and what I'll so let me do that. So sigma I equal to 1 to m fi h xi into phi is equal to phi, okay. I get this just by multiplying both sides by phi, and then I use the fact that you know you see phi is gxi by hxi on dhxi, but if I cross multiply I will get phi times hxi equal to gxi, not only on dxi I will get it everywhere, okay. So I am using the following fact: if two polynomials are equal on an open set, if two polynomials treated as functions they coincide on a non-empty open set, if the two functions defined by two polynomials, if they coincide as a function on a non-empty open set, then the polynomials are equal, okay. So what this equation tells me is that on this non-empty open set dhxi the function phi times hxi and gxi they are the same, okay, and I want to say from that they are the same, phi times hxi and gxi are the same if you want as regular functions on the whole space. So I am using, so in fact let me restate it more correctly. I am saying that if you have two regular functions which coincide on an open set, then they have to coincide on the whole space. If two regular functions coincide on a non-empty open set, then they coincide on the whole space. The reason is topological. The reason is because regular functions are continuous and open subsets are dense. It is very simple. The reason is topological, okay. So if two so all I am saying is that if I have two regular functions, okay, and if the fact that they coincide on an open set means that the difference regular function is 0 on an open set, okay, alright, but the set of points where a function is 0 is a closed subset because a function is continuous. Therefore this open subset is contained in a closed set, but the open subset is dense, which will tell you that the open subset that it will tell you that these two regular functions are the same everywhere, okay. So let me write that down so that you know, okay, so let me rub this side. I still want this side of the board, so let me write that down so that it becomes clearer to you. So what I do is, here is a lemma. So here is a lemma 1, any regular function is continuous. So here is a lemma, any regular function is continuous. So you see, so what is the proof? So the proof is take psi in O of u if you want, okay, or let me take O of something, okay, so let me take O of u, right. Then so psi is actually a map from u to k. Psi looks like g mod h locally, okay, where you know G and H are polynomials, they are polynomials in the right number of variables, and you are considering U inside that affine space, okay. And then you see, to show psi is continuous, it is enough to show psi inverse of a closed subset is equal to a closed subset, okay. All right, so psi inverse of a closed subset of here is a closed subset of K and is a closed subset of U, this is what I will have to show, all right. But then what is a closed, you know the Zariski topology on K, which is A1. The Zariski topology is just the complement finite topology, namely the only closed sets of finitely many points. So psi inverse of a closed set is just psi inverse of finitely many points, and to show that is, and psi inverse behaves well with respect to unions. Psi inverse of a union of sets is the union of psi inverse of those sets. Psi inverse behaves well with respect to the operation of taking unions. So to show that psi inverse of a finite set of points is closed, it is enough to show that psi inverse of a single point is closed, okay. So enough to show psi inverse of a point lambda in K is a closed set, a closed subset of U. This is what I will have to show, okay. So but you see, but then given X in U, there exists Gx Hx with X belonging to D of Hx, and psi is equal to Gx by Hx, okay. So what this will tell you is that, you know, it will tell you that so in a neighborhood of X contained in DHX, this is the definition, local definition, all right. But then psi inverse of lambda intersection this neighborhood is just Gx mod Hx inverse lambda in intersection this neighborhood, and this is just equal to Z of, so Gx mod Hx has to be lambda, so Gx has to be lambda Hx, so Gx minus lambda Hx has to be 0, so it translates to Z of Gx minus lambda Hx intersection this neighborhood, which is of course closed in this neighborhood, okay, and you are done, because you know, to check that a subset of a topological space is closed, it is enough to check it on an open cover, okay. So what I have done is, I have, for every neighborhood, every point I have shown that psi inverse lambda intersection that neighborhood is a closed subset in that neighborhood, okay. And if I vary X, I get an open cover, and for each of the sets in the open cover I have verified that the inverse image intersected with that set of the open cover is a closed subset, okay. So this proves the lemma. Now let me prove another lemma, which is the lemma that I want to apply there. So of course, you know, I am looking at regular function on either on an affine variety or a quasi affine variety, mind you, okay. So So here is lemma 2. In fact, yeah, if two regular functions agree on a non-empty open subset, then they are equal. If you have two regular functions, they are equal on a non-empty open subset, then they are equal everywhere. Proof is 2 lines. Proof is trivial. Two functions agree on a non-empty open subset means the difference function is 0 on a non-empty open subset, but any non-empty open subset is dense, okay, for the Zariski topology. So you have a function that is, you have a continuous function that is 0 on a dense open set, so it has to be 0 everywhere, so it is obvious. So proof is any non-empty open subset is dense, and it's just, and a function which is 0 on a dense, a continuous function which is 0 on a dense open subset has to be 0 everywhere. Simple topology. So if you apply these two lemma, I mean I need this lemma. Now you look at this equation that I have written here. In this equation, you know, if I look at the product hxi times phi, the product hxi times phi is gxi on dhxi, okay, but hxi times phi is also a regular function, it is a product of two regular functions, and gxi is also a regular function because you have already seen every polynomial is a regular function. So you are saying the regular function phi times hxi is equal to the regular function gxi on the non-empty open subset dhxi, therefore by this lemma it is the same everywhere, therefore for hxi times phi I can put gxi, okay. So what I will get is I will get sigma I equal to 1 to m fi gxi equal to phi, and that tells you that phi is actually that polynomial given by the left side. That is a polynomial that I wanted, okay. So now let me continue. So let me rewrite that, sigma I equal to 1 to m fi hxi phi is equal to phi. This is equality as regular functions, okay, but hxi times phi is the same as gxi because hxi times phi is equal to gxi on dhxi and therefore on whole affine space because of this lemma. Therefore I can replace hxi times phi as gxi everywhere. So what this will tell you is that it will tell you that phi is actually sigma I equal to 1 to m fi gxi, and that is the end of the proof. I have proved that the regular function is actually the function that you get by evaluating a polynomial. What is that polynomial? Here is the polynomial, okay, that is the proof. So you see there is a tricky bit of commutative algebra coming inside the proof, okay. So the moral of the story is there is no difference between the ring of regular functions on affine space and polynomials on affine space, okay. So every regular function on affine space which is defined locally by gluing polynomials, by gluing quotients of polynomials, if you take a regular function on the whole affine space which you have gotten locally by gluing quotients of polynomials, the resulting regular function is actually a polynomial. What that means to say is that it is the function that is gotten by evaluation of single polynomial, and that this is that fact written in the form of an equation, okay. So you do not get anything new, okay. Now you can use the same technique of proof to prove the other statements, okay. All the time you will use this fact that whenever the corresponding space is contained in a union of finitely many basic open affines, then the corresponding equations, polynomials that occur in those that define those basic opens, the ideal generated by that is unitary, that is the key, and then from that by applying this lemma you can get the proof for all the other cases, okay. So in the case of so in all these cases your regular functions agree with the ring of functions that we defined, the coordinate ring of functions that we defined. Okay, so I'll stop here.